Welcome back. So we have the formula that we had just derived in the previous video. This is that how fast you need to launch something squared is equal to 2 times the gravitational constant times the mass of whatever you're launching and divided by the radius of that object. So in other words, mass of a planet over the radius of the planet, or mass of sun over a radius of sun. So there's speculation, and the evidence first shows up that the speed of light is actually a constant in 1870s is the first bit of evidence for that, but it takes 30 years for anyone to really accept it, and even then there's still some fighting with it because, well, naturally anytime there's a paradigm shift. But Einstein in 1905 comes out with his idea that if the speed of light is constant, there's some repercussions from that. So one of the repercussions of if the speed of light is constant is that anything starting slower than the speed of light will never actually get to the speed of light. Anything starts faster than the speed of light will never actually get to it. It is a barrier. So if we are talking about anything that we are trying to launch, actually anything with mass, speed of light is a barrier here. And so I can find out the radius of an object needs to be a black hole just by solving for r here. So the radius of a black hole is going to be 2g mass of the object over vi squared, which, if the speed of light is a maximum limit for our things, for stuff that we can do, this would be over the speed of light squared. So c is the speed of light. If this is the first time you're familiar with that notation, just E equals mc squared is an equation that most people are familiar with, or with which most people are familiar. And so that c stands for the speed of light, which is approximately 3 times 10 to the 8th meters per second. Now there is an exact figure because the meter is defined based upon that. So speed of light is an actual constant, and it's down to to the ones place. However, that's good enough for what we're doing right here. So the question I first ask is, how big does the Earth need to be in order to become a black hole? So if we took the current size of the Earth and suddenly shrunk it down, how small do we need to make it? So that would be 2 times 6.67 times 10 to the times 10 to the negative 11th. Times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, over the speed of light, which is 3 times 10 to the 8th squared. And so this is the radius of the Earth as a black hole. So 2 times 6.67 negative 11 times 5.98 24 divided by, if I can do that in my head, 9 times 10 to the 16th. And we get 0.00886 meters. This is a radius here. This is the radius of the Earth in order to become a black hole. Now, so that is 8.86 millimeters. And so the diameter of the Earth, if it became a black hole, would just be double that. So instead of thinking, I'll just do that, 0.0177 with rounding meters, or 1.77 centimeters. So if the Earth could somehow magically keep its entire mass but shrink down to something down to about that distance between my two fingers right there, and if I'm going to get closer here, I definitely need to be a little bit more precise there. There we go. The distance between my two fingernails there, then it would become a black hole. In other words, in order to escape it, something would have to travel at the speed of light. Now, the fact that the Earth would become a black hole is ridiculous. That's just not going to happen. And so let's do it again, except this time for our sun. Well, the only thing that's changing here is this value right here. And so this is for Earth. as black hole. And so now let's do the radius of the sun as black hole. And so we have 2 times 6.67 times 10 to the negative 11th times the mass of the sun, which I think is 1.99 times 10 to the 30th, but let me look that up. Yes, I remembered correctly. So 1.99 times 10 to the 30th kilograms divided by the speed of light squared. So I should just be able to take that number. And then divide by 5.98, 10 to the 24th. And then multiply times 1.99. The 30th. And what we end up with is 2949.6 meters. In other words, a little under 3 kilometers. If the sun shrunk down to something a little less than 3 kilometers, it would be a black hole. Now, according to our current theory, our sun shouldn't do that. It's too small. If you think about a sun, what we have here is a process where you have a bunch of hydrogen atoms joined together. When they join together, they create helium atoms and they give off energy. And so we have, and that energy is now trying to radiate outwards. And so there's 2 factors involved in stars. We have this, according to our current understanding. There's this gravitational pull trying to pull it in, and then there's this radiation pressure trying to get out. And so as the sun burns, it loses a little bit of mass. But we have this radiation pressure outwards, and we have the pull inwards. Now, when the hydrogen runs out, then we're going to have to go to the next level of atoms. So helium probably will be the next most common bonding. They'll join and they'll create, looking at a chart over there, create beryllium, or maybe the hydrogen and helium will combine to create a lithium. Anyway, we'll get heavier and heavier atoms. As the smaller ones get used up, we'll go to larger atoms in order to fuse and create and give off energy. As they are giving off energy, as we get the larger and larger atoms, less and less energy is given off when they fuse. So, and this goes, I think it's up to iron. Anything at iron is basically the break-off point. Anything above iron, in order to give off energy, it needs to split apart. This is the fission. This is the basics of the atomic bomb. Anything less than iron needs to fuse in order to give off energy. This is the essence of the fusion reaction, or the essence of the hydrogen bomb. So, since there's less and less radiation coming out as we get to larger and larger atoms, the gravitational pull starts to have this effect on it. So, but you're losing mass every time you give off radiation. And so if it's like our sun, what is expected is that we'll lose mass faster than the radiation pressure, and so so our sun should expand. Now, sometimes I'll hear that eventually we'll be inside the sun. That is not the case, because as the sun loses mass, our orbit will start to move out farther. So according to theory, eventually our sun will be where we are right now, but the Earth will be farther out. Now, if it is massive enough to start with, so we're talking red giants, if the red giant starts out, when it starts to lose, it will eventually collapse in on itself. And various things happen depending upon how big, and we start getting into astronomical terms, and I get a little weak there. So there's super red giant, they're large stars. So some of them will collapse and create something incredibly dense. Some of them will collapse down to such a small amount that they will become black holes, and some of which will collapse down and they'll come in so fast that they will then explode, and then we get the novas and supernovas. And I did not do that in any particular order, so that is just sort of where things are. So anyway, this radius right here is known as the Schwarzschild Radius. And that's the German soldier who happened to be a theoretical physicist who worked on general relativity while recuperating. He ultimately does not survive the war, I believe he actually doesn't get out of the hospital, but he does have a lasting amount, the Schwarzschild Radius. This is where the event horizon occurs. Sometimes you might hear the term event horizon. That's basically the edge of the black hole. One other thing about black holes, some miscellaneous bits, is that black holes, there's an incredible amount of energy going around a black hole. If I have a particle if I have energy, right, some sort of radiation that can spontaneously produce into particles, if it produces the particles small enough so that they're moving fast enough, one of them will potentially get sucked into the black hole and the other one gets sent outwards. The stuff being sent outwards is something that is, and I'm going to mangle the terms here, but it is something, this is basically the essence of Hawking radiation. This is one of the signatures that we were looking for a black hole, is the stuff that from this pair creation, that part of it gets sucked into the black hole, part of it gets sent out. Now, as this happens, because we are losing mass in the general vicinity, eventually black holes, unless they get enough mass to replenish it, black holes will eventually dissipate. There's a video put out by Melody Sheep, about a half hour long, talking about sort of the future of the universe, and they sort of go into some of that and I recommend it anyway. It's not a happy-go-lucky video, but it is really interesting to me. Another thing about black holes, sort of miscellaneous topics here, if our sun somehow, all the theory is wrong, the sun somehow becomes a black hole, what would the Earth do? It would still continue to orbit. The mass of the sun hasn't changed, so the Earth will still just go around fat, dumb, and happy. Now, we would lose all light, and so our days are numbered here. Now, we would not die instantly. The Earth does give off some of its own heat. I mean, we have survived winters before, but at some point, the plants would all die, the animals would die. We'd have flashlights. I guess there's greenhouses, so as long as the electric plants last. Some of this might be addressed in there's a book, as well as there was a documentary series, can't remember which one, about if all the humans disappeared, what would happen? Even though it's not the same problem, it touches on some of the same basic situations about how long things would last without human intervention. So with a human intervention, assume it's going to last a little bit longer, but the end of basically all life on Earth. There's probably some bacteria that'll survive. We're not going to last too much longer. I have thought through it at one point and I came up with a month, but that's just pure speculation. I don't think it would be days. I think we could survive longer than that. And there you go. There's my spiel on black holes.